Hi, welcome back. The last video cut off a little bit short, but luckily it stopped right before we started this example here. So we're going to continue on with example B from question 2. So here we have g of x equal to 1 over x plus 3 minus 2. I can see from this that my base function for f needs to be 1 over x. So what this means is that g of x is equal to 1 over x plus 3 minus 2. It just means that it's taking this base function 1 over x, and there's some transformations that are happening to it in order to get what we have up here. Let's try to write those out. So if I were to give some instructions to obtain g of x, I would say take f of x, but we're going to need to do a couple things with it. So you can clearly see from here that in f of x we have x, but I wish to get x plus 3. So I want to go from here to there. So what I should say is, how about we switch f of x to x plus 3? Okay. So what this means is, whatever you have in the bracket here, that's what we have to substitute in for x. So that will actually work out pretty good if we put x plus 3 in here, because if we put x plus 3 into that x, we end up getting this part of g of x. Okay, so all I'm trying to do is come up with basically a set of instructions of what to do to f of x in order to get this. So then we just have minus 2 at the end, so we can write minus 2, and we can call this one done. So this is the transformations described in function notation. So we say a new function g of x is equal to a base function f of x, but we're gonna transform the x part in here, and we're gonna subtract 2. So if I can check this, I can verify this real quickly. You don't need to do this, but if you write out f of x plus 3, you can actually go ahead and plug this into x in here, and you get 1 over x plus 3. So notice this looks a lot like this here. In order to get the same thing, we just got to subtract 2 on both sides. So f of x plus 3 minus 2 would be equal to 1 over x plus 3 minus 2. Okay? And we can see that this is actually just g of x. So that means g of x is equal to f of x plus 3 minus 2. So that's exactly what we said here. So we know that this is okay. This set of instructions can easily take 1 over x and turn it into this. Now I'm going to write this, I'm going to compare this to our general form where we have, that's a minus d, x minus d plus c, but that shows the parameters d and c. And by doing that, I can easily determine what c is. So I could say c is negative 2. That means we're going to end up shifting down 2 units. And I can also see that d must be negative 3. In order to get x plus 3, d should be negative 3. So let's state those. We can say there must be a horizontal shift of 3 units left. And there must be a vertical shift 2 units down. Okay. Notice how I keep this kind of consistent. I first say the direction, horizontal or vertical, then I say the type, the shift, and then I just say the number of units, and then I say what direction, left or right, or up or down. So that's describing the transformations using words. And this one is describing the transformations in a function notation, as the question was asking. Now for the graphs. Let's start with the base graph. F of x equal to 1 over x. I'm going to plot some points for that, some ordered pairs. So I need to pick some negative ones, and I also need to try to get close to 0, because we know that 0 is undefined, right? If I plug that in for x, 1 over 0 is undefined. So I'm going to write that in here, undefined. And then I'm going to pick some positive ones, a half, 1, and 2. The reason why I picked these 3 is because I'm going to have a piece of the graph over here, and I'm going to have a piece of the graph over here. So I need to have at least 3 on each side in order to establish something that can help let me kind of see what's going on to visualize it. So let's get started with plotting. Well, we have to calculate the y values, but at this point, let's actually look at the this part when x is 0, when it's undefined. So we know that x cannot be 0, so that means there can be nothing along this line here. So what I like to do is I like to show this as a vertical asymptote. So going through here, and we will label this as our VA, and we'll say x equal to 0. That's the equation of that line. So the VA, that just means it's a vertical asymptote. Okay, that's a boundary line with the graph. The graph basically cannot cross it, and also no points can exist along this line. The other one I'm going to point out is the fact that 1 over x, that can never actually equal 0. So 1 over x, no matter what you put in for x, this can never equal 0. So that helps me establish the HA, which is the horizontal asymptote. So that means that, I'll do this one in green, that the graph will actually never hit the x-axis, because apparently, according to the equation, it can never equal 0. So I'm going to label that one right here. I'm going to call it the HA, and I'm going to write x equal to 0. That's the equation of that line. So as hard as these types of functions are, there is a little bit of simplicity attached to it. So knowing that you got VAs here and here really help you with the graph. Now it's just figuring out where the other points are. So let's calculate them. Kind of going back to this, what we started earlier. We're going to plug those into x. So we'll get negative a half for the first one, then negative 1, then negative 2. How did I get negative 2? Well, 1 divided by negative a half is negative 2. The smaller the denominator is, the bigger the value of it is, or the bigger the expression is. So, all right, now the positive one's underneath. So 1 divided by a half is 2. 1 over 1 is 1, and 1 over 2 is a half. Let's throw those points down in the graph. Let's start with the top ones. Negative 2, negative a half, that will be here. Negative 1 is here, and negative a half, negative 2 is right there. Okay, I can start to draw this curve. Oh, try that again. Now, the behavior of this is that it's going to keep approaching the VA, and this will keep approaching the HA. And I'll kind of show you how that works later. Let's just plot the other side. So now we're doing these points, a half, 2, 1, 1, and then 2, a half. Alrighty, so we'll look at this on Desmos. So going back to here. So what does the function do as it gets closer to the asymptote? So let's start, let's actually start this way. So what does the function do as x gets really big and negative? So numbers like negative 10,000. What will the y value be? So we can easily just kind of plug these in. So if I put in a large number like negative 100, we can see I have a small value of negative 0.01. And as I make that denominator approach negative infinity, so if I go more out that way to larger negative numbers, I just get smaller numbers like negative 0.0001. So we can see why this kind of starts to hug the horizontal asymptote or the x-axis. Now coming in this way towards the vertical asymptote, those are numbers that are getting closer to zero. They're still negative though, but they're getting closer to zero, like negative 0.1. See, that's negative 10. If I add a zero in here, negative 0.01, well, that's getting even closer to the y-axis. And now it's saying it's negative 100, like way, way down here. Put in one more zero, we get negative 1,000. So you get the idea. You can see that, yeah, okay, as we get closer to zero for x, the y values are continuing to decrease down negative infinity. Same happens on the positive side. If I get rid of this negative symbol, then we just get positive values. So numbers that are way up here. And then as we approach positive infinity for x, so like as we go out this way, we're going to put in numbers like 10,000. We're going to see what y does. So put in like 10,000, and you can see we get smaller numbers. So it's going to keep getting closer and closer to the x-axis as we go out. And that makes sense, right? Because remember what I said here? The smaller these numbers are, the bigger this is. The bigger these numbers are, the smaller this is. So kind of has like almost like that inverse effect. Okay. So those are the base points. The question wants us to graph the transformed points, transformed function g of x. So let's write out g of x here. I'm actually going to do this in red. Erase this here. So we'll do it in g of x. So I need to take all these nice points. I'm just going to lower them a little bit. I want to map them over to new ones. So I need to do a horizontal shift of 3 units to the left. So I got to take all my x values and subtract 3. That way they're shifting to the left 3. Then I got to take my y values, and those all need to go down 2. So I'm going to write y minus 2. Okay. This is an algorithm to calculate all the new transformed points. So I'm going to take these x values, and I'm going to plug them into x, and I'm going to calculate them all down here. And then I'll do the same thing with y values, calculate those all respectively as well too. Okay, substituting in negative 2 for x, we'd have negative 2 minus 3, which is negative 5. Then plug in negative 1, we get negative 4. Okay, I'm just going to go ahead and do the rest. Negative 2.5, 1 minus 3, negative 2, 2 minus 3, negative 1. Now for the y values, plug in negative 1/2, negative 1/2 minus 2, that's a negative 2.5. Okay. And I'm just going to go ahead and do the rest in my head. Negative 3, negative 4, undefined. If you plug in undefined, and for y, you're still going to get undefined out. Okay, plug in 2. 2 minus 2 is 0. 1 minus 2, negative 1. 1/2 minus 2, negative 1.5. So these are all my new points. So I'm going to go ahead and plot those first. Negative 5, negative 2.5. We have to zoom in a bit here. Negative 5. So we got 1, 2, 3, 4, 5. That's right here. Negative 5, and it's at negative 2.5. So that'll be right there. Then we got negative 4, negative 3. That would be right here. And then we have negative 3.5, negative 4. That would be there. Negative 3 is undefined. That's going to be my new VA. So at negative 3. And let's go ahead and do the other side. So these here, negative 2.5, 0. Negative 2.5, 0. Negative 2, negative 1. and -1, -1.5. That would be about right here. Okay, what about my HA? Where's the new horizontal asymptote? Well, if the graph shifts down 2, that means this just bumps down 2 and it's going through here. And you can see that works with our points. If I draw a dashed line at -2, you can see it goes between the two sets of ordered pairs. Sorry, that's not x, that's y equals -2. Y equals -2. Okay. And I can do the same thing. I can just make my graph hug through here. It's going to have the same shape. It just changed position. It moved to the left 3 units and it moved down 2 units. And that is the graph of g of x. Last thing we had to do in this question was state domain and range. So I will do that up here, the domain. Actually, let's do the base graph first. So the base graph, the domain, x is an element of R, and x cannot equal 0. So I'm looking at this black one, the original one. Okay, the only value of x that was restricted was the VA, where we said that x can't equal 0. Right, that was right here. The range, well, we have every y value except for 0. Remember, 1 over x cannot equal 0. And now for the transformed one, g of x, we have x is an element of R, x can't equal -3. And that -3 comes from the horizontal shift of 3 units to the left. Okay. We can also see it satisfies the equation. -3 would be a restriction for this because we do not want to divide by 0. And the range, y is an element of R, y cannot equal to -2. So remember, this shifted down 2 units, so we will have no y values at -2 for g of x. How does that tie into the equation? Well, if this can never equal 0, then g of x can never equal -2. Okay, so this number here ends up being our horizontal asymptote. And from our restriction in the denominator, that's how we get the VA. So this ties in with the domain, and this one ties in with the range. All right, that is it for the rational functions. Okay, moving on to our next example. Okay, this one will be a little bit easier. Actually, let's do this in blue. We're going to first state our base function. So this time, I can see here we got a square root function. So this must be referring to the base function root x. So what do we need to do to f of x in order to get g of x? So if I'm trying to obtain this, g of x, what do I have to do with f of x? Well, I can clearly see that this needs to turn into an x minus 2. So I'm going to replace x with x minus 2. Okay, remember whatever is in here gets substituted in. And then we can just add 4. So this shows the transformations in function notation. This tells me the instructions on what to do to f of x in order to get g of x, this up here. Okay, I can verify this real quickly. So f of x minus 2, that means I take x minus 2 and I plug it into f of x and the x in the root. So we would have root x minus 2. Okay. Notice this looks almost like that. We just got to do one more thing. We got to add 4 to both sides. Add 4 to this side, that means you got to add 4 to the other side. So now this tells me exactly how to get g of x. You do f of x minus 2 plus 4. So we can see that worked. Okay, now we need to compare this to our general form, x minus d plus c. And I can clearly see that d is 2 just by comparing those. And I can clearly see c is 4. Okay, remember d is always the opposite of how it looks in the bracket. D is 2. Okay, because d is 2, we're going to have a horizontal shift. And it's going to go to the right 2 units. And then we're going to have a vertical shift up 4 units. Okay, let's write out our base function. Base function is root x, and let's establish some key points. So because we're square rooting x, I want to use positive and perfect square numbers, like 0, 1, 4, and 9. Plugging those in, I get 0, 1, 2, and 3. Okay, we only look at the positive value when we're square rooting because this is a function and our output can only have one value. So we take the positive ones. Plotting those points, 0, 0, 1, 1, 4, 2, 9, 3. And this is f of x equal to root x. So you can memorize these, you can write these off to the side and keep them handy because these are the points that get transformed. These are going to map over to x. We're going to the right 2, we'll say plus 2. And we're shifting up 4, so we'll say y plus 4. Substitute all the zeros into x, and calculate the new points. We'll have 2, 3, 6, 2, 3, 6, plug in 9, 9 plus 2 is 11. Okay, substitute in these, and for y, and calculate all the new ones. 0 plus 4 is 4, 1 and 4 is 5, 2 and 4 is 6, 3 and 4 is 7. Let's plot those points. We got 2, 4 for the first one, 3, 5 for the next one, 6, 6 for the next one, and 11, 7. That would be right there. Okay, notice 0, 0 was my start. My new start is now 2, 4. So we're going to begin at 2, 4, and we're going to draw this through those points. That is g of x. Notice the shape did not change. All the points just moved over. They moved up 4 and over 2. Okay, we can see that with all of them. Up 4 and then over 2. Just like this one here, up 4 and then over 2. So it is exactly like the same shape as the other graph. It's just been shifted. I'm just going to erase those. Okay. So this ends up becoming g of x, those points. Okay, we're almost done here. We're just going to state the domain and range. I actually started to do this one earlier. This is the domain for the transformed one. Okay, it says x greater than 2, greater than or equal to 2, y greater than or equal to 4. So the transform graph, we're greater than or equal to 2 because we start at 2 and go this way. And the y said the range, sorry, which has to do with y, it begins at 4 and then it goes up to positive infinity. So that's how we get the domain and range here. We still need to do it for the base function. So the base function, we can say domain, x is an element of R, x is greater than or equal to 0, because that starts at 0 and then works its way out. The range, y is an element of R, and y is greater than or equal to 0. So that starts here and then works its way up. So we can see how the transformations play a role in the domain and range. So notice the transformed one, it goes from 0 to 2. Well, that's because it's shifted to the right 2. Our range goes from 0 to 4. That's because it's shifted up 4. Okay. So we can see even in the equation, like this is our equation for g of x. Our domain, this 2 comes from here. Basically, it's what makes that start at 0. And the 4 comes from this part here. Okay, that is it for 2.3. I will see you guys in the next lesson.